Let's learn how to calculate the half-life of a substance and do half-life calculations. First of all, our definition here. The half-life of a substance is a measure of how radioactive it is. It's the amount of time that it takes for half of my sample to decay. And so let's say the half-life is 5 seconds. Well, that means that in 5 seconds, my original substance, half of those nuclei have decayed into something else, and half of them remain. And we have a little point of clarification here. It says each atom in a radioactive sample has a 50-50 chance of undergoing nuclear decay. And so what I have here is a screenshot from what's called a PhET simulation. And we've got this bucket of polonium here. And what we've done is added polonium into the sample. And I let it go for roughly 1 half-life. Okay, and so I pushed play and the polonium decayed. And what our slide says is that each atom has a 50-50 chance of decaying. And so it just means that it doesn't matter which atom you're looking at, each one within the span of one more half-life, in this case it'd be something like, if I push play and let it go for this long, well, each one of these has an equal chance to have shot off, in this case, an alpha particle to become lead-207. That's another important point, is that when these nuclei decay, they don't disappear, they just turn into something else. And so it's just the amount it's the amount of time it takes for your substance to half of it to turn into something else is the half-life. I've got one more thing for you before we solve our problems. This is an equation, and if your problem didn't end exactly on 1 half-life, you're going to see that our problems tend to be really conveniently even splits right down the middle of a half. But if you had a messier problem, this equation could get you the answer that you're looking for, no matter what your data is, as long as you had sufficient information to solve the algebra problem. I'm going to leave that for you to look at if you want to, but let's look at the type of problems you'll need to be able to solve for our Chemistry 1 class. Okay, I have a specific format, and I'll label it after we solve a problem. So let's look at an example here. It says if 100-gram sample of an isotope with a half-life of 10 years, so let's kind of underline our important information. I've got 100 grams. We know the half-life is 10 years, and we know it's going to decay for 30 years. And so what's my ending mass? What mass remains? All right, let's start. Here's my format. I like to start with my given amount, whatever my starting amount is. And so in this case, I'm starting with 100 grams. Okay, so we've got 100 grams. We put a decimal in there for significant figures. And so my 100-gram sample. And then I like to draw an arrow to show that it's undergoing 1 half-life. Above the arrow, I like to write which half-life we're talking about. This is the first one. And under the arrow, I like to write the length of that half-life. In this case, that would be right here, 10 years. So 10 years. So it's showing me that 100 grams, after its first half-life of 10 years, it took 10 years, how much will remain? 50 grams. I'll keep my 3 significant figures here. 50 grams, because half of it has turned into something else. The other 50 grams is some other isotope, depending on the type of decay. Okay, well, I've undergone 10 years, but how long should I go? Oh, I'm going to go for 30 years. All right, well, I got to go again then. So here's my next half-life, my second half-life. That was another 10 years. And how much remains after that 10 years? Well, 25 grams. Well, that's 10, 20 years. Looks like I'm going to undergo one more half-life. My third half-life is going to be 10 years, and that's going to be 12.5 grams. And that was the question that we were asked, is what's the mass that remains? And in order to answer that question, we've answered that question. 12.5 grams remain. The reason I like this formula of showing the number of half-lives, of half-lives above and the length of the half-life, length of half-life. The reason I like this format is because just it gives you a nice orderly way to solve a lot of different types of questions. Let's say instead it gave you the original amount and your final amount. Well, if you just lay it out in this format, then you can solve for how long the half-life was or how many half-lives it underwent. Okay, so it just gives you a nice framework for solving. Let's do the next one, and then I'll let you solve some on your own. It says the half-life of an isotope, we'll do this one in green, is 30 seconds, and at the end of 3 minutes, 25 grams remain. What was the original mass? Oh, well, this is going to involve a little critical thinking. So let's start with the original mass, which we have no idea what that is. So let's just put a box here. This is going to be some amount of grams. It looks like this is where our unit is grams. Well, we know that it's the half-life is 30 seconds, and we're going to go for 3 minutes. So let's just put our information, the information that we have. So the half-life is 30 seconds, and it turned into some amount. 30 seconds, 30 seconds, 30 seconds. That's, let's see, that's 1 minute, 2 minutes, we need 3 minutes. 30 seconds, 30 seconds. And so it looks like after 1, 2, 3, 4, 5, 6 half-lives, we have we've let this sample go for 3 minutes. And what other piece of information do we have? Well, it looks like we end with 25 grams. Well. If we know that we end with 25 grams and every step of the way we divided by 2, could we reverse engineer and figure out how much was in the original sample? I believe you can. I'm going to let you take it from here. Happy solving.